Okay, and if you watched the video yesterday, I think the very last thing in the video, or one of the very last at least, was talking about this idea that sometimes you are given this coefficient of determination. And again, if you didn't watch it, I'm going to be using some terms you're going to be a little bit unfamiliar with. This is our R squared right here. So, and you can use a capital R, lowercase r, you'll see it both ways, but whatever the case, this R squared, this coefficient of determination, and that's going to be an important thing for today to understand. This basically says 54% of the variation in your Y value is explained by the variation in your X value. It's kind of a weird way of saying it, but all right, we can talk about that more. All right, let's just jump into this. R squared is exactly what it looks like. It is the square of your correlation coefficient. So if I want to get the correlation coefficient, and I need to do that in order to find the slope, then I want to do the square root of 0.54. Now, before I do that, just to explain why I need correlation coefficient, remember your slope B is equal to the correlation coefficient times the standard deviation of Y over the standard deviation of X. And this was from time doesn't mean anything anymore because of all the snow days. I think it was Thursday or Friday we talked about that. Friday, I think. So jumping into this, if we do the square root of 0.54, we get 0.7348. Now I'll just cut it off there. Now, the main idea from what we talked about yesterday in that video is that this is not necessarily correlation. This is not necessarily your correlation coefficient. What we need to do is we need to figure out, should it be a positive or a negative correlation? So what we're correlating here is the number of times someone solves a Rubik's Cube, and I should have looked at it up here actually. The number of times someone solves a Rubik's Cube and the time it takes. So here's what I would think. If I am using the number of times as my explanatory variable, number of successes, I'll just put S, and then time. So the more that someone solves this, the faster they should go. So the higher the number of successes, the lower the time will get. So I'm actually looking at a negative correlation between these two. And in this case, negative is a good thing. We want our time to go down. All right, so I am not going to call this 0.7384. I believe this is a negative 0.7348. I mixed my numbers up a second ago. Negative 0.7348 correlation. And the only way that we can know that for sure is by looking at what we're correlating together, and we have to kind of intuit and reason our way through it. All right, so now we can get to the end. I'll just do the math. I can plug this negative how do I want to do this? Negative 0.7348 times standard deviation of Y is luckily given. I know that time is my standard deviation for Y, that's 24. And the standard deviation for X, the number of times is 138. That's the standard deviation for it. Those are just given to me. So this is the calculation I need to do. And when I do that, I actually haven't done this. So I'm sure some of you have. Anyways, I got, oh, I put the wrong, no, I didn't put the wrong numbers in. I did, I put my wrong numbers in, I'm sorry. Sorry, you get to watch me do some math that you've already done. Times 24 divided by 138. So it's going to be B actually. So a lot of you knew how to use this, but you forgot to turn it into a negative correlation. If you still have questions on that, we can come back to it, but hopefully you guys see that B should be the correct answer. Now, if you got C, that means you were doing almost everything right. You just mixed up on one part. That's an easy fix.
Mr.
Okay. So there's a lot just to talk about conceptually with this, and this is very much a conceptual chapter. We're looking at chapter 9, but I honestly can't recall right now how many calculations we might need to do out of this, but we're good. Let's just start talking about this. Oh, I threw this one in as a, I say fun in quotes. This is an interesting type of problem that, okay, I'm just gonna run through how to solve this, but I want you guys to look at it for about 30 seconds. And I know I can go somewhat fast, and sometimes people need longer to process than what I give you. But what I wanted you to look at just enough, I wasn't asking you to try and solve this in 30 seconds, but I wanted you to just look at this problem for long enough to try and even figure out what it's asking you to do. And the problem here, if you've been keeping up, you know that you can solve for the exact regression equation if you know the correlation coefficient, but it doesn't tell us what the correlation coefficient is. So we have to approach this very conceptually. Okay, so let's try and figure out what we know. Okay, so here are my two equations that I know. Well, not including this. Here's my regression equation. And I want to figure out which one of these right here might be the one, or at least a possible one. I know that my slope is the correlation coefficient times S sub y over S sub x. And I know that y bar equals a plus b times x bar. I know that the regression line has to go through y bar and x bar. Now, from this table, the only thing we know is S sub y and S sub x. So I'm just going to plug those in real quick. So r is unknown, S sub y is 3, S sub x is 0.75. So if I divide that, I get 4 times r. Again, it might not seem like we're making any progress here. I'm going to go ahead and jump down to the next one. I know that x bar and y bar are given. So I'm going to plug those in. I'm going to have 5 for y bar equals a plus, I'll just plug in x bar real quick. I'm skipping over the other. So I might just take this slope right here that I found and plug it in. 4 times r. All right. So one thing I do know, actually, let me backtrack a little bit. I don't want this 4r to be in there. I'm just going to put the b, okay? Here's one thing we know about the correlation coefficient. What are the possible values of my r value? What's the possible range, rather?
-1 to 1.
-1 to 1. So that is telling me that the absolute biggest slope I could have is 4 times 1. So my max is 4 for the slope, and the minimum is -4. So my slope has to be somewhere in that range. So I can look over here and I can rule out any problem or any one of these answers that doesn't have a slope somewhere between -4 and +4. So that means this one right here, this one right here, those two will not work. Now, this -4 does technically work, even though it's highly unlikely. So now we need to figure out what can we do to figure out the correct one of these three. Well, I know that the line has to pass through x bar and y bar. So that means I need to find which of these three equations right here will work for a y bar of 5 and an x bar of 4. So if I try this, let me just take this first one. I'm going to try 5 equals 13 minus 2 times 4. And 13 minus 8 is 5. Hey, what do you know? That one works. Looks like I have an answer. I'm just going to put a circle around that. That one's tentatively correct. But I have to make sure that the other ones aren't. All right, so let me try this. If I erase all this right here, let me try this next equation. So y bar is 5 equals -9 plus 4, because there is no slope on that one. -9 plus 4 is -5. -5 and 5 are not the same, so that one doesn't work. All right, and last one. So I can actually cross that one out. So I'll just try this last one. It looks like we already have our answer, but in due diligence, I'm just going to run through all of them. All right, so y bar equals 16 minus 4 times 4. And 16 minus 16 is 0. 5 does not equal 0, so that equation doesn't work either. So the only one that worked was B. And again, I think this is a really interesting question because you really have to dig deep into the theory and the concepts behind it. But there you go. Okay, so I forgot about that little practice problem I threw in there. But now let's look at, this is from chapter 9. This is almost like a smorgasbord of different ideas about scatter plots that are just covered. All right, are there any questions before we move forward?
How did you know that R was between -1 and 1?
That's just one of the rules about correlation coefficients. A -1 would be that situation where every point falls exactly on a line, and that is a perfect negative correlation. Now, the positive one is the opposite, where you have every point falls exactly on a line. That's a perfect positive correlation of 1. So in this case, R would be 1. It can't go any higher than that.
Gotcha.
Okay. Okay, so subsets. And again, if you read the chapter, you're already familiar with this to some degree. So in a large data set, sometimes there are subsets that make that up. And now I did pull these photos from different data sets, but let's just pretend real quick that we see this original scatter plot, and we have, when you look at the residual histogram, and you can take all your residuals and you can put them into a histogram. And let's say it was bimodal. Well, maybe what that means is that there's actually 2 different trend lines that are parallel to each other. And so all these residuals right here would live right there. And then all these residuals right here would live down here. All right, so it's, if you can follow kind of visually and conceptually what's happening, sometimes you could have 2 different subsets that are meshed together, and you can figure out that there's kind of a categorical difference between these 2. So these subgroups aren't necessarily revealed by residual plots, but if you categorize your data at the beginning and run regression analyses for each subgroup, then you can sometimes see those trend lines. Here's the example from the book where they talk about different breakfast cereals. And some of them, you know, you can see the bottom and middle shelf basically could be grouped together. There's not much difference between those 2, but the top shelf actually has a lot more calories for, I can't see what that bottom is, per gram of sugar. Okay, so if you read the chapter, you can kind of get some more digging into that. But notice if you didn't have these data points separated into those 3 different top, middle, and bottom shelf, then it would just look like one cluster of data, and you wouldn't see any of those distinctions between them. Okay. Now, I will add to that, you are not going to have to go into the deep analysis with that, generally speaking, but you just need to be able to speak to it on a conceptual level. So I'm never going to give you a data set and say, categorize all these data points and then replot them individually. That's a lot of work. So instead, you would be given a diagram like this, and have to speak to what's happening. Explain the diagram. Okay, extrapolation. And this is one you might have been familiar with even outside of this class. So regression models are really useful for making predictions, but there's an appropriate way of using them. And that is whatever your original data range was, it's most appropriate to use the model for prediction only within that range. And that is called interpolation. You've probably heard that term before. But if you decided to extend your model beyond the range of the data, you're introducing uncertainty. And we don't know what's happening beyond your max because we don't have data on it. So we can only guess. And if you go too far away, it can be very unreliable, and that's called extrapolation. Generally speaking, it should be avoided. Now, if you only go slightly beyond the min or the max, if you went from 1 to 100 and you tried to guess what 105 was going to be, that's not the end of the world. But if you went 1 to 100 and tried to estimate what 1000 was going to be, that would be not very appropriate. So you can see this is they call this, there's actually this right here, heteroscedastic right here is a fancy word that says the variance around this doesn't stay the same. Very low here, but very big over here. That's just a fancy stats word. If you take stats in college, you'll get to learn all kinds of fancy words. Okay, but notice, pretend that this is the end of your data. Your cone of uncertainty, and that's another term that's sometimes used, as you get further away, you have way more uncertainty way out here. But just a little bit past your data, it's not so bad. But generally speaking, you don't want to extrapolate. Okay. Oh, I just revealed the surprise if you saw that second graph. So this is data. I believe this is also from your textbook. And so you will recognize this if you read it. But you have this trend from 1980 until 2000 on the price, I believe this is of oil. And so if you were in the futures business on oil as a commodity and you're trying to figure out, is it wise to invest in that? You know, whatever the case, you could project certain things. Here's the actual price in oil that happened at the year 96 or something. And you can see it spiked all the way up to $100. And this, I remember this is when I started driving, 2001. And I remember buying gas for $1.30 per gallon. And then in a few years, it was up to almost $4 per gallon. So that's just my own personal story there. But yeah, price of oil did not follow any projections. You can see what the experts at the time projected the prices to do. All right, this is if you are familiar, you should have heard of Hurricane Katrina, the one that hit New Orleans. You're probably familiar with that. So what this is showing is the same kind of thing. Here is where the hurricane was at this particular forecasting time. And they thought the hurricane was going to go and hit around over here. But this gray area around it is actually their cone of uncertainty. So it could have gone at an extreme. It could have followed the very end of this and hit way over here closer to Western Louisiana. Or it could have made its way all the way over toward like Pensacola. So they didn't know where it was going to hit, but they thought it would be somewhere in this range. And all this is showing is also, notice that from 2005, that was their cone of uncertainty. 2015, their methods had improved, and now they're way more accurate. But still, they don't know where it's going to hit exactly when you're that far out at sea. Okay, that's enough on that. But here's one last fun extrapolation idea. All right, this is the biggest conceptual thing from this chapter, I think. Outliers, leverage, and influence. And these are almost like pretty fluid concepts, but hopefully we can define them clearly enough that you know when something is an outlier, when it has leverage, and if it's influential. Okay, 3 factors can affect our model. Outliers, high leverage points, influential points. Okay, and leverage is, I think, a pretty straightforward concept. Leverage, and just think of it like a lever. In fact, who was that philosopher that said, give me a lever big enough and I can move the world? You might have heard that phrase before. But basically, A lever lets you minimize your work if we're getting into physics. So if you have a lever right here, and you might have even done, I'm getting kind of a bit off topic. I mean, not, or just digging too much into the topic, but there's this place I've been to where they have this, like, it's a truck. So I'm just gonna draw this box to represent a truck. And this lever that moves way over. And you can, as a person, you can just pull on this, just pull it down, and then you're picking up a truck. All right, so if you have high leverage, that gives you a lot of power over what you're trying to lift. All right, some physics in there, but that explains why we call this leverage. If you have a data point that is pretty far removed in the x direction from all your other data, it is going to be considered a high leverage point, because wherever this point right here ends up, if it's up or down, it's going to have, it can have a big impact on the overall trend line. So leverage is always referring to how far is this X value from the main clustering of the data. So in something like this example, this particular point would be a high leverage point. This one right here is not considered high leverage because it's still in the X direction, it's still sitting right in the middle of all the clustering of data. And of course, we'd call that an outlier. We'll talk about that one next. But high leverage just means there's a big gap in the X direction from the rest of the data. Okay, now a point can have high leverage without changing the model. It does technically change it. We'll talk about that more. But notice this trend line is already running this way, and this point happens to fall pretty close to it. So it's not really changing the model that much, but it does still have high leverage. We'd still call that a high leverage point. So this one's not high leverage. So it does affect the model somehow, so we would call this an outlier. And we already said that. So a little bit more. What a high leverage point will do regardless is it will affect, even if it doesn't affect your trend line. So adding this point right here, like we said before, really isn't affected by that point. It's still going to go the same direction, but our correlation coefficient and therefore our coefficient of determination are going to be impacted by this, because this reinforces the correlation. And it's going to, you know, before we are at a 0.96, maybe it went to a 0.98 now. And that might not seem like a lot, but it does affect it. It does affect your correlation coefficient. All right. Outliers. So we would consider an outlier to be a point that does not follow the general trend line shown in the rest of the data, and it's going to have a large residual when the least squares regression line is calculated. So you can pick those out really well on a residual plot. So if you had a residual plot and a bunch of points, your outlier is going to sit somewhere off of that. Okay. So of course, we already talked about it. This is not an outlier since this is going to be a pretty low residual. And we have to be careful with the idea that a big residual means it's an outlier, but it isn't going to follow the main trend line. Okay. So just like our high leverage points, we can consider those with a big difference in X. Here's my change in X. If I had a point right here, this compared to the rest of the data would have a big change in the Y direction, and that would be an outlier. All right, it's probably clear enough. All right, so what I want you to do is find any outliers and find any high leverage points. And you can circle them. Yeah, go ahead, circle what you think an outlier is here. All right. So we got those outliers. And then what's going to be a high leverage point? There it is. I see the L. So I'll assume the L is for leverage. Okay. So the reason hopefully the way we're going through it, it's very clear distinction, but it can be kind of confusing if you look at just a bunch of points and you're asked, what would you describe this point as? High leverage, low influence, stuff like that. So just try and keep these ideas straight. All right, so a point has leverage if it's separate in the x direction. It's an outlier if it's separated from the trend line in the y direction from the trend line. You have to be careful about that. And a point can be an outlier and not have high leverage. So here's your data. This is a low leverage or no leverage outlier. This one over here would be a high leverage outlier. And hopefully you can see the difference. Here's the main clustering in our x direction. There's a gap here, but there's not right here because that point falls right in the middle of it. Okay. If it is an outlier and has high leverage, it will have an even bigger impact on the regression model than if it was just an outlier without high leverage. That one's probably clear enough. Just like we thought about the idea of the lever to move something very heavy. If you're far enough away and you're an outlier, you're gonna mess things up. So this is what we would call that. That is an influential point. If you have a point that changes the regression model greatly, if it's removed, then that's an influential point. So let's give an example of what's not influential. All right, if I had all this right here, I'm going to add one. I know it's kind of hard to see these points I add sometimes, but I have that blue point. Might be a little hard to see. If I removed that blue point, it would barely impact my correlation at all. And the regression line probably wouldn't even notice it. So no influence or very little influence. Okay, an outlier is often influential, but it can be mitigated or almost completely negated if there are many data points and it's just a moderate outlier. So let's look at an example of that. So if I've got a bunch of data points, and they are very tightly packed around this line, I'm just adding so many right here, and I have one outlier that lives right there. Even though that's an obvious outlier and we all identify it, we also might find that if I ran this regression line with that point in it and without it, that it doesn't change that much because I've got hundreds of data points that follow this line really closely and just one outlier. So is it really influential? Probably not. It's being drowned out in all the rest of the points. A high leverage point is sometimes influential. We saw one earlier that fell right in line, so it didn't have really any influence. But it also needs to be an outlier and kind of be separate on the trend line. So if I took this high leverage point and moved it down here, then all of a sudden, that is actually going to have a big effect on my regression line. Now it might run something like this. Okay, it wouldn't look like that exactly, but you get the idea. I changed my regression line quite a bit. Oh, let me go back. All right, hopefully this is all clear, but are there any questions on this? Okay. Again, we can come back to this with any questions. So here we can see visually with the actual regression coefficients. So notice you've done these printouts before. You've seen your A and your B. A is your y-intercept, B is your slope. Actually, no, in this case, sorry. They did it with an AX plus B. We don't do it that way, but you can do it on your calculator. A in this case is your slope, B is your y-intercept. Here's the original data. And now we're running the regression line again with this point added. So my slope changed from 0.886 to 0.871. So this really didn't change it that much. My correlation coefficient went from 0.99 to 0.93. Yes, it changed, but is this a big enough change that I really say this is an influential point? I probably wouldn't. I would say it's not influential, but it is an outlier. If we look at the next one, well, no doubt about this. When you see your regression line, this is definitely changed. So the blue dots are still the original. But now this point was added, and look at how that's changed. Our slope has changed greatly. Our y-intercept has. Our correlation coefficient dropped all the way down to 0.24. So this is a major influential point. It's high leverage, outlier, influential. Okay, this one is high leverage, but not influential in the sense that it follows the same trend line. It changed my slope slightly and the y-intercept slightly, but it didn't really do much else. It did strengthen my correlation. Now it's at 0.993 instead of 0.987. Okay, and lastly, here is an outlier with no leverage really, but it does change my slope enough and my y-intercept that it has a big effect on the correlation coefficient, and it just changes everything. So with these examples, hopefully you can see distinctions between all the different possibilities. And there are others, of course, we didn't cover here. Okay. Are there others? I don't know. I didn't think through that before I said it. Maybe there are others we didn't consider. So now here's what you get to do. Here are 4 data points. I want someone brave to add to this an outlier that's influential and has high leverage. So even though this point could end up lots of different places, we can see a general trend line that looks like this, and that's definitely high leverage, and it's definitely far removed from where we'd expect it to be. So very good. That will work. I will clear my drawings. I'll leave those points up there. Here's your next one. I want the same, it's the same 4 points, but I want an outlier that's influential with low leverage. So those look all pretty good to me. With only 4 points, you know, it's easy to have influence over that. And I see some clustered down in the bottom left, some at the top right. And when it says low leverage, and this is only a distinction we'll talk about here. I can't imagine this would ever matter on the AP test. There's low leverage and then there's no leverage. No leverage, of course, would mean it's in the middle of your X values. Low leverage might mean it's just slightly beyond. So maybe these points could move a little bit over and have low leverage, but I'm not really trying to dwell on that point. But yes, you are right. These are outliers. They are influential. That's definitely going to change your regression line. And yeah, you put them where they'd have low leverage, maybe no leverage, but you get the idea. So those are good. Next one, outlier with no leverage. Pretty straightforward. This doesn't look much different, except that leverage is a little different. No leverage, everyone's putting it right in the middle, and that's good. I didn't draw that line straight, but there we go. Those are outliers. It doesn't say anything here about if it's influential or not. So, you know, you could have had a little bit of leeway on that, but those are all good points that fit. Not an outlier, not influential, and low leverage. See if you can figure that one out. See if I can. Yeah, we can see even this one that was just added over here. I think that would even work. It's not an outlier. It's not influential. So we know it's going to fall on that line somewhere, close to it. Low leverage. It might fall just outside of those points. But again, I'm not splitting hairs on that part. So yeah, if you have points that live somewhere around here or somewhere around here, that's good. I think, how many more do I have? At least this one. So try this one on. You guys are getting pretty fast at this. So I see a bunch of points that are on the trend line, high leverage. I saw a couple, one placed down low, one placed high. Even this one is probably far enough that you can consider it high leverage. There's no cutoff point between low leverage and high leverage. So I'm not looking for a specific number of spaces away. But we can see that all works. Of course, what is the one thing that does change for sure with a really high leverage point like this one?
The correlation.
The correlation, very good. So adding this point will change your R and of course R squared, but your y-intercept and your slope might not change at all. So very good. Last one, question mark? No, there's not. Okay, that was it. I forgot if I had 5 or 6. All right, so that's kind of the big takeaway. If you can get all 3 of those straight, you're in good shape. All right, correlation tables, I think is the last thing we need to talk about. So with correlation tables, there's one other thing. Anyways, correlation tables, this is where if you notice what's going on, we've got, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9 variables that are all being correlated. We have this matrix of correlation happening. And these colors represent the highest correlation. All of them are pretty high. None of them get low, but it could go down to -1. Of course, if you notice, always to vote in elections, that's going to correlate perfectly with itself. So you're going to see a 1.0 along this diagonal. Now, here is the danger in something like this, because you could just look at this and you could pick out what are the highest correlations. I see a 0.96 right here. I don't know if there's anything higher. There's another 0.96. Oh, there's a 0.97. Anyways, we could look for really high correlations. Even the lowest correlation here is like 0.87, 0.86. Oh, sorry, that was the wrong spot. All of these are pretty high correlations. The problem is just looking at your correlation coefficients tells us nothing about the shape of the scatter plot. These could all be correlated really strongly while looking like this. You know, so it got some kind of a exponential curve to it, but we're just looking at that right there, and that's, you know, that correlates pretty strongly. So if we look at just correlation without anything else, we run into the danger of thinking that this is a really strong relationship right here, and in reality, it's not an appropriate model. Okay. Again, there will only be conceptual questions in any way related to this. So that means you're not going to have to do too much with something like this, but it's a good concept to understand moving forward, because you'll almost certainly have to deal with statistics in college, and you will almost certainly see things like this. So that's just a way of being very critical about what you're seeing and thinking through it. All right, there we go. We need to know that the association is linear. Okay, now the last thing mentioned in the chapter, I think I'm right this time, is the idea of using summary statistics in lieu of the original data, and you use those summary statistics to create a scatter plot. So this is not good practice. And why is that? So I'm going to talk about it here, and then we'll kind of visually see it in a second. Using summary statistics is going to artificially inflate the correlation and give a false impression of the explanatory effects of the model. So those might just be words right there. Let's kind of see what that means in practice. This is actually from the textbook. So when we say we're going to look at summary statistics, I've got all these different heights. So if I look at only the people who were 64 inches tall, I could take those and I could come up with a Y bar for 64 inches. So Y bar sub 64. And the average weight for someone who is 64 inches tall is given by that data point right there. So this is not an actual data point from an individual. This is a summary of however many people that is, 6 people. Likewise, I've got this outlier right here, but he's just going to be, he or she will just be added into, let's see, 1, 2, 3, 4, 5, 6 people being averaged together, and that's 71 inches, I think. So that's this data point right here is now the average of everyone 71 inches tall. So if I did a regression analysis on all these original data points, I would get an R squared of 41.5%. But when I do the correlation or the regression analysis for that on the right, it's an 80.1% coefficient of determination. And again, 80.1% of the variation in these summary statistics is explained by a difference in height. But only 41.5% of the variation in weight is explained by individual differences in height. Okay, so this is a form of manipulating data to artificially improve the power of our model by almost double, and it gives a very misleading picture. So generally speaking, we do not want to use summary statistics. All right, so hopefully this is all good. You're able to follow along. I know I ask a lot of you guys every day to really keep your brains working. And we're going to cap this off with one problem that is mostly conceptual. All right, so we're looking at people swimming across Lake Ontario. Why anyone would want to swim across a Great Lake is beyond me, but whatever. People do it. And it happened 42 times between 1974 and 2006. There's even a website that tracks this. What is wrong with people? All right. We might be interested in whether they are getting any faster or slower. Here are the regression of the crossing times in minutes against the year. Okay, and we're actually only looking at the residual plot as far as this goes. We're not seeing the original scatter plot. And remember from the printout, we know that the intercept, this is our A, right? And this is our B, or slope. Okay, so what does the R squared mean for this regression? And here's the R squared. Anyone want to take a stab at that? So we can say 1.3% of the variation in time is explained by the variation in year, or one of the other examples there. I'm just going to clear everything and we'll move ahead. Are the swimmers getting faster or slower? What do you think?
Aren't they getting faster because the slope is positive?
So the slope is counting the number of minutes. Would we want a positive or a negative slope?
We want negative.
It'd be negative, so it's actually
Right.
getting slower. Though it is a good thought. I'm glad you caught onto the slope being positive. It's just now in this context, faster would mean we're getting slow, or it's going down. So the outlier, anyways, you can see someone did a round trip. Apparently crossing once wasn't stupid enough for them. So they did a, and for some reason they just kept the total minutes of the round trip. Anyways, would this change the model? We're not even going to answer that because we're going to move on to number 28, where they come back to the same thing, and they did remove it. And you can see what changed. That changed to that, that changed to that. Okay, so here are your new numbers. Don't worry about these other things. We're going to come back to this one at the very end of the semester. And when I say the semester, I mean April. Okay, in this new model, the value of S sub E is much smaller. Explain what that means in context. Now that's what I guess we do need to worry about a little bit. S sub E, so I tell you not to worry about it, and I tell you to worry about it. This is something that you learn. This is your standard deviation of your residuals. So if you have your residual plot, and you've got your residuals right here, you can create a histogram out of that. I'm going to say all these residuals, you have like plus a little, minus a little. I could create a histogram that looks like this. And most of the residuals are going to fall pretty close to the line, but I'm going to have some that fall away over here. And I can basically come up with my standard deviation, which is S sub E. And that's from chapter 8. So if you need to go back and review that, that's good to do. So if my S sub E is much smaller now, what does that mean in context? I'll just answer this one for you. And I hope I'm not taking away your ability to kind of process through it. But if my original had, well, let me actually, get rid of some of these points. Not that I need to, but I had this one big outlier right here. And what that did is it took the standard deviation, and you can think of standard deviations like a line above and below, where 68% of the data is going to fall between these two. But now I've got this one right here, and that stretches the standard deviation out. So now the average distance away from the regression line is much smaller. There's less variation in the data as far as from the trend line. The distance from a data point to the trend line is much smaller. I'm saying this different ways. You could also say the residuals are smaller on average. Lots of different ways of saying it. All right, now would you be willing to say that Lake Ontario swimmers are getting faster or slower? So what do we think? To interpret our slope, we might say that every year that we move ahead, we add 6.17 minutes to the time it takes to cross Lake Ontario. All right, and that's what we've got. So they are getting slower. All right. So again, conceptual questions abound. And okay, I forgot about this. I added this question. So if someone swam the distance in 1,075 minutes in 1980 and another person swam it in 1,150 minutes in 2000, whose achievement was more remarkable, statistically speaking? Okay. So what we've got here is we've got two trend lines. No, we've got one regression equation. And this, just to walk through this one pretty quickly, what we're saying is what residual is more impressive? Okay, so I'm going to predict what time it should have taken someone in 1980. So according to, and I'm using this model for it. So my A is there, this is my B. So it's going to be negative 1,148.7 plus 6.17091 times the year. I can't even fit that on the screen. Okay, there it is. So if I do that for 1980, I'm just going to do this on the calculator, but not write it out. All right. It looks like I would predict someone would finish that in 1980 in 1,169.7 minutes. So this is y hat for 1980. I can do the same thing, a y hat for 2000. And if I do that, I'm just going to plug in 2000 for my x. And I'll do the same thing. I get 1,293.1 or 0.12, but it's fine. So whose achievement was more remarkable? If someone swam it in 1,075, then their residual is just the actual minus the predicted. So the residual for, I'm just going to put resid for 1980 was 1,075 minus 1,169.7. Their residual is a negative 94.7. They swam it an hour and a half faster than we would have expected. But in 2000, even though it took them longer, let's see what theirs is. 1,150 minus 1,293.1. gives me a residual of negative 143.1. So yes, while this person in 2000 swam it slower, compared to what we'd expect of them, they actually swam it over 2 hours faster than we would have thought. Even though it's not a great model, we're still going to answer this. Okay, so hopefully that made sense. If you have any questions about this, please let me know. And sorry if you were trying to get caught up. I can come back to that. I just wanted to let everyone go who is feeling good about today. So there you go. You've got your homework. We're just going to be practicing for the Unit 3 test, kind of covering up some other random things tomorrow. And hey, you've made it over 200 pages in the textbook. Way to go. So if you don't have any questions, you can have a great day. If you do, you can feel free to stick around, and I will see all of you tomorrow.